There we go. Cool.
Somebody kind of the lights right there, see which ones. Nobody? There. Definitely turn on the one that says whiteboard. And I think of the one that says inboard. Yeah, try one more. Yeah, all right. All right, let's take a look here. So removable ones means that it already meets the requirement that the limit agrees. It's just that there's a hole then that could be moved, that could be filled in. So this is like the pothole crew came out, there's a hole, they dumped the tar over here, they didn't fill the pothole in. Good job, guys. But this is still removable. They could come and say, let's pick this up and put it here, and then the discontinuity is gone. A jump is one that has no chance. There's no way you can connect those by just defining what a point is somewhere. There's no way. So this, at x equal -3, there's a jump discontinuity. At x equal to 6, there's a removable. And then here, there's like, I can take two different types. Technically it is a jump, but I would accept infinite also. It's like an infinite jump. Yes?
Is there a specific one that you prefer?
For that problem, not really. It's a slightly evil problem because it's a mixture, so I would take either one. Like I said, though, jump is technically what it really mostly is. Okay, like this. Okay. This guy, a lot of you guys, I love the fact that one of you guys asked me this, which is a great question. How the hell do I do this? But you said a little more specifically, you said, do I do the function values first? I would always do the function values first because they're like completely knowns. They're your anchors, right? So put in there, -3 goes to 2, 0 goes to 0, 2 goes to -1. And now like pick one of these. So there's only problems at -3, 0, 2, and 5. There's limits. So as I approach -3 from both sides, I should be approaching the output of 2. So as I come from this side, I'm going to 2. And as I leave it, I should leave from 2. So from both directions, it's coming there. So is that a discontinuity at -3? No. Now what's the next point? 0. That's the next place anything talks about. The limit as x goes to 0 from above is -1. So as I go to 0 from above, I should be approaching -1. And from below, I should be approaching 1. So as I come from below, I go to there. And as I go from above, I go to here. Let me stop here for a second. As far as how you draw the lines, you can do almost anything except make it not a function anymore by curving back on yourselves. Here. Yes? Say it one more time. All right, so if there's a limit approaching an output, but there's no function value there, that output doesn't happen for the function, and there's an open circle there. So I put all the closed circles down to start with. So this was a closed circle because it was closed to begin with, and the limit just happened to come at it. This is a closed circle, but the limit here doesn't come at this, and the limit from above doesn't come at that. So these are open circles. Did you guys see that? The limit looks like it's going somewhere, but it doesn't get there. That's the idea of an open circle. Okay. So what about if I move on to 2? As I go to 2 from either direction, the output's supposed to go towards 0. So what kind of thing is going to be at 0 there? So at 2 is supposed to have an output of 0. And this is supposed to be closer. There we go. So now As you approach 2 from either direction, the output is 0. Stop there. You guys cool with that? That limit doesn't have a plus or a minus on the 2, so as you come from either side, you're supposed to be approaching 0. Do you actually get there? No, you already put a point there. So it's got to be an open circle. And now the next weird place is 5. As you approach 5, does it say from which direction? From both directions, you're supposed to go to negative infinity. So what's going to be at 5? Well, asymptotes. And then you just got to go to negative infinity. So that is one possible answer. Right? Is it important that this did this? No, you could have it going, whee, whee, straight. It doesn't matter. You can even just have a little arrow, which is okay, because it's like, I didn't tell you what's happening back there. So you're either allowed to do whatever you want to, or go, I ain't going over there. I don't know what's over there. Cool? Like we're going west, because we all kinds of weird shit going on. All right, any questions on that one? I do like that kind of problem, so I'll put that on there. Obviously, I like this kind of problem too. Now, number 3. I wanted to see what you guys would do. Which one of those functions has a problem based on where it's defined? 1 over x, because x can't be 0 for that. So that's obviously somewhere where it's discontinuous, because you can't put 0 in that function. What would it be? What would the limit as x goes to 0 be? Careful. Doesn't exist. Why? Because from below it's negative. So for you guys, it would be this, like that, right? I can't chew gum and do this. Is everybody cool with that? So 0 is definitely a discontinuous place. I like the way I said that. Any problems with x up there? Any problems with rad x minus 1 considering where it's defined? No. Right? Rad x minus 1, what's the smallest number you could put in there? Better than me, because this is all about real stuff here, right? You can put a 1 in there. It's the smallest one and have a real output. Thankfully, we're allowed to use things starting at 1. Okay, that jives. So 0 is a discontinuous place. So where's the only other places that might be discontinuous? Yes, the meeting points. The joints of this thing, they connect them and weld them together. Are they like, bleh? So at negative 1, do they line up? What is g of negative 1? What is g of negative 1? Which thing are you looking at to answer that question? X, because that's working for negative 1. So g of negative 1 is negative 1. What's the limit as x goes to negative 1 from above? Let me write this stuff down. So I know 0 is a problem. What is g of negative 1? Negative 1. What's the limit as x goes to negative 1 from above on the other side? Negative 1. So is it continuous at negative 1? Yes. Because not only is the function defined to be negative 1 there, but it's also the limits match up. Stop here for a second. So you look at the functions that make up your piecewise, and you say, do any of you have a problem by yourselves? Considering what x's you're allowed to use. That was like the 1 over x. Then you look at where they're supposed to connect. Do they actually connect or not? Now, where's the other place you got to look at? 1. What's g of 1? Which function am I looking at? Good, because that's where, if x is 1, I'm allowed to use this. So what's g of 1? 0. Well, what's the limit as x goes to 1 from below? So what am I going to use now? 1 over x, because that's the one that works for x is less than 1. X is really close to 1. I use this. And what is that limit? As x goes to 1 from below, what's the limit? 1. So is it continuous at 1? No, this would be a jump. Discontinuity. So it's funny, I'm asking where's it continuous, so it must be continuous everywhere except 0 and 1. Because those are the places where it had trouble, where they didn't match up. So really, please, let this make sense. A function by itself can have problems, like 1 over x. A piecewise function inherits problems where it's trying to change from one function to another. So in real life, what is a piecewise function all about? I got a rocket going up, it's following a certain trajectory, there's a function that defines it, and then a meteor hits it, right? Now it's following a different function. So for x less than 5 seconds, it follows this function, and then x greater or equal to 5 seconds, that's when the meteor hit, it follows some other function. That's piecewise in real life. So yes, they are real life interpretations. If you have something that's like teleported, well, that's funky as shit. That's what we call that removable discontinuity. There's no way. Here's somewhere right here, and now we're right here. What the hell just happened? Right? Okay. Any questions about that? There are going to be piecewise functions in the homework, obviously. You desperately need to understand them better. I'm worried if your pre-calc teacher sort of like skipping by. If that's true, go find them and slap them. Okay. All of these are probably does not exist in some way, but you can be more specific sometimes. Now help me out. What does a natural log look like? As x goes to 2, what is the inside doing? It's going towards... As x goes to 2, the inside is going towards 0. I like it. So, in fact, the inside's always positive. Is that cool? Because I'm going to 2 from above. So 3 squared minus 4 is positive. And then I'm getting to 2 squared. It's always positive. What's natural log of x look like? What's it look like? What's ln of x look like if I graphed it? You guys just draw it for me. Careful, that's exponential. That's still exponential. I love you guys. Yeah. What's happening right here? That's 0. Asymptote. I love it. Doesn't reach it. And it's going towards what? Negative infinity. So the better you know what the functions look like, which is what pre-calc is supposed to do to you. When I teach pre-calc, I tell them this is graphing hell. You guys remember, do you agree with me? Have you gone through pre-calc? Hopefully. What the hell are you doing here? Would you agree with me that one way to define it is graphing hell? Or maybe you love graphing, which is beautiful, but most students normally don't. And don't we just analyze the shit out of graphs? Do you guys not remember this? So I tell them it's graphing hell because when you get to calculus, you want the calculus to be the problem, not the graphs. The graph should help you, not hurt you. You should know what every function you've talked about so far looks like. And the more you know what they look like, the easier these questions are. I know some of you guys are like, oh, graphic calculator knows what they look like. I'm not going to let you use a graphic calculator all the time, so you better know what they look like too. So this answer is negative infinity. Don't just say does not exist. It's got to be more specific. What do I do with this guy? Holy shit. When I put a 3 in, what do I get? Yeah, so it's 0, 0. So I got to do something. This is just yelling at you what to do. What do you do? Yeah, you factor it. Cut to the chase. So one of these cancels. Now what do you get when you put a 3 in there? Yes, so now you've got to stop and say, okay, it's going to be some kind of infinity, possibly. It is specifically coming from above, although that looks like, I don't know, sideways, perpendicular. It's supposed to be a positive sign. It's way over there. So as I go from above, what sign does this have? Because I'm using numbers that are bigger than 3, subtracting 3, that's positive. And the top is around 3, so that's also positive. Therefore, the answer is positive infinity. And again, get used to putting that plus sign so it's really clear to me that you know which infinity it is. Well, up here I'll make it C. All right, and then part C is probably the one you like the best. What does cosecant look like? What's cosecant related to? It's 1 over sine. So if you graph sine, right, what is this? Here's sine, right? This is sine. What is this? Pi. Pi is negative. Blah, blah, blah. So I'm all curious about pi, right? From above, to be honest, so I better go further. So how do I do cosecant? Who remembers how to draw cosecant really quickly? You just sit the cups on the top and bottom of those hills, right? As sine goes to 0, cosecant goes to infinity. That's why this works, of course, right? So here it's going to be a cup down, isn't it? You guys remember that? That's how you get cosecant and secant very quickly. Don't memorize them. Draw their reciprocal function and then sit the cups on the hills, right? Ooh. Because the idea is that. It's beautiful. So what is happening then, now you got to keep, the x comes in, but isn't that, what's true about x? It's always positive, right? As I'm going, I'm going towards pi. So x is positive around pi. What is cosecant as I go to pi from above? Yeah, going to negative infinity. So the answer here is negative infinity. I could have been really evil and said x goes to negative pi, because then this would have been negative, and that would have changed the sign of what that was. But here, that's positive. Whatever this is going to is what the whole thing is going to. It doesn't change the sign of that infinity. Does that make a little bit of sense? All right. Or a lot of sense with it? Okay. So can you turn the lights back on? We're going to do the other side in a bit. I got to explain to you how this proof stuff works. There are a couple things from section 2.5 to finish up. Stop that. Okay. What were they? What? Oh, just stuff like here. Yeah. So here's an example of something that's a little bit unfair. So we have an automatic way to take care of it. If I look at square root of x, and I say, what's the limit as x goes to 0? Now, technically, in order for this limit to exist at any point, it has to agree from both sides. Now, what's a little evil about that? Since we're only talking about real stuff, I can't go to 0 from below. So I don't even have to put a plus. It's just understood that I'm going to come from their side that works. So at endpoints, when it's the end of the domain, we consider the limit from one direction only, the side where the domain actually lives, the x's you're allowed to use. So I only consider from above. Of course, that's 0. Is that cool? So that's limits from one side or the other. Then not only just something I can do to you by putting a plus or minus in there, sometimes it's just what's fair for a function. I mean, like, functions have been screwing me away, won't it be fair to them? Okay, that's one idea. Another idea is, nah, don't want to do that. If f and g are continuous, let's see how specific are they? Yeah, sure. At a. Oh, let me just say at a. Then, so is f plus g, f minus g, f times g, get out of there, f of g, f times g, c times f, cg. Right, so if f and g are both continuous at a, then obviously f plus g is continuous at a. If they're both well-behaved, when you add them together, you get another well-behaved function. right? So is the difference, so is the product. Now what is it about the quotient? Of course, same thing as before. So f over g is cool as long as g of a is not equal to 0. Yeah, actually. G of a. So this is saying the limit of these at a agrees with the function value there. So as long as g of a is not 0, then this limit also exists. I like it. And again, a lot of this is sort of commonsensical, hopefully. And then finally, here's the big bad awesome theorem. If you have your book, it's theorem 7, page 120. Let me get an idea here. Where is x plus 1 over x minus 7 continuous?
All values except 7.
Beautiful. I love it. Right? In fact, what is it about 7 that shouldn't even bring it into play? What's the domain of this thing? All values except 7. So it's any rational function is going to work the exact same way. Are you guys, any polynomial divided by polynomial, it's going to be continuous everywhere on its domain. Same thing with radical functions. So this theorem 7 says these functions are continuous everywhere on their domain. Polynomials, obviously, right? When we first defined polynomials, your teacher should have said, one reason we call them this is because they're nice. They're well behaved, right? Rational functions, root functions, trig functions, they're continuous everywhere on their domain. I like it. Inverse trig functions, exponential functions, logarithmic functions. Those are all continuous on their domain. Now there was, just to go back, there was a problem in chapter 1 where the people who said graded, you're not showing me enough work, the answer sort of magically shows up. This is a bad habit to get into. Don't do that. But there was something that looked sort of like this, I think. I think I have a problem like that in it. And you had to find its domain. Which would also be all the values where it's continuous. Now we know that too. That's what this theorem does for me. Those types of functions, once I figure out the domain, I figured out where they're continuous. They're the same thing. You guys with me? So polynomials, root functions, trig functions, rational functions, all that kind of shit. Once I know the domain, that's the same place where it's continuous. All right. How the hell do I find this guy's domain?
Simplify the expression that's in the brackets, or in the brackets.
True, but what do I set up to work with? What's got to be true? What's got to be true about natural log of x? Knowing the picture. What's got to be true about x? Greater than 0. So what's got to be true about the input? Greater than 0. So that has to be greater than 0. Now there's two ways to do this. One way is this is a parabola. It's an up-opening parabola. Where will it be positive? I don't know, do you guys see how you can look at it that way? I'm going to show you a different way to look at it, but isn't this an up parabola? Where does it go through 0? Negative 3 and 3. Where is it positive? That's what this is saying, isn't it? Where's that parabola positive? Where's it positive? Below negative 3 and above 3. Right? It's only negative in here, so you got to throw those out. That would make the natural log freak the shit out. And 0. Right? So this would be, the domain would be negative infinity, negative 3, or 3 to infinity. You got to throw out everything between negative 3 and 3. It would freak the natural log out. Another way to do this is one way. That's a smart way. Less work to do because you know what things look like. You can solve this directly, but you got to be a little careful. This is where everybody kind of does this weird shit. That's not true. What is the square root of x squared? It's not x. Square root of x squared is? No, come on. No. What's the square root of 9? Is it plus or minus 3? No. So the square root of x squared can't be plus or minus. The square root of x squared is absolute value. because the answer to a root has to be positive. Right? And I don't know if I've told you this, but when I see absolute value inequalities, when I teach these, the greater than are restraining orders. This says the distance has to be greater than 3. Stay the hell away from me. So here's 0. It's got to be start at 3 and go up, negative 3 and go down. That's exactly what we got. Greater than 3. Stay the hell away from me. You can stay more than 3 feet away from me. That's kind of a pathetic restraining order. They can still throw shit at you. Anyway, it's the idea. So you got to have a way to do these. And if you don't know how to do them, don't get the answer some other way. Go, I want to know how the hell to do this. Let me ask. Shit. That's what you should be doing. If you don't know how to do something, find out how. Don't just find the answer and go on. I'm going to put this stuff on the test. The quiz. Shit. Okay. So. Oh yeah, we'll do that. Yeah, we'll do that last. Let me go back. We're going to do 2, 4. Yes?
Just to clarify, the quiz isn't this Thursday, it's next Thursday?
This Thursday.
This Thursday?
Yes. Yeah. Chapter 1 should be done. If you're not done with chapter 1, it's not late yet, but you are starting to fall behind. Right? You should be into chapter 2. 2.1, 2.2 should be done by Thursday or close to it. If you're nowhere near there, jump ahead. Do some out of 2.1, some out of 2.2, so you're ready for this quiz. If you haven't got the book yet, and that's why you haven't done chapter 1 homework, I put chapter 1 homework on the website, so don't give me that. Right. You do want to get a book, though. Yes?
So is the chapter 1 homework just the chapter 1 review?
Yeah, the problem was from the review.
And then it was like 2 and that's it?
No. What do you mean?
No, like, so we had the chapter 1 review, and then we started chapter 2.
Into chapter 2, yeah. Yeah, 2.1, 2.2. You can get ahead, which is great.
More chapter 1.
Yeah, there's one assignment from chapter 1. Yeah. Chapter 1 was like a review of algebra and pre-calculus. That's all. All right. Yes, sir.
For the book, we can get the smaller one if we're just...
Yes. So I sent an email out trying to clarify that the one they have in the bookstore, I think, is the one for all 3 calcs. Right? If you don't have to do all the calculi, then just get the little one that works for 1 and 2.
And that one's also in the bookstore, right?
I don't think so. But if so, it's awesome.
Well, I rented the same.
You're into the big ass one, right?
Yeah.
Okay.
It's like $20.
Yeah. So, I mean, if you've got access to one or the other one, that's great. If you want to pick one, the smaller one should be cheaper, I would think. So you can get either one. You can always come see me if you're having trouble getting the book, and I can print out some more homework sections for you. I'm not going to do that the whole semester. Right? Because they're also in the library. They're in the Math Study Center. You can check them out. Cool. I like it. So no excuses about homework. You should be in there no matter what. Anything else before we get into this proof section? Okay. All right. So, this is section 2.4. It's called epsilon delta proofs. So there's the symbol epsilon, and there's the symbol delta. I like it. When we start it, it's going to sound insane and crazy and hard. And then once you do a few problems, you start to see they're almost all the same thing. So it becomes almost too easy. You guys don't believe me right now. But I love that it's sort of a setup for a baby little proof, just to get used to it. And like I said, these guys are going to show up throughout the book. So if we understand what they mean right now, you'll know what they mean as you read the book later. As they point out certain theorem proofs, you'll know what the hell they mean. So, if a function has a limit at an input, and it exists, this is almost going to be a little bit silly. What's that mean if I get really close to A? What do the outputs eventually have to do? The outputs have to get, not small, it's not going to 0, close to L. If they never do, how the shit can this be the limit? Right? So if my function outputs never get close to L, how could L be the limit? There's no way. So help me out. How would I draw this? So the limit is x equals A of f is L. So what am I going to put in A? Possibly in open circle, possibly. Or it might be filled in, but right now, if that's all we know, I can't put a closed circle there. We'll stop here for a second. We just did this earlier when we were graphing that thing with all those conditions. Right? We really did. Some of you guys look unconvinced. Or barely awake. So I know, and since that limit exists, that means as I approach from below and from above, it's got to be going towards that. So on one level, this definition, this idea that as my inputs get close to A, my outputs must get close to L. So this is a way to make that close more formal. Because what the hell is close, right? If you were to guess somebody's weight and you were only 5 pounds off, that's pretty close, right? But if you're guessing the weight of an ant and you're 5 pounds off, that's far away. How much is ant weight? 5 pounds, 1 gram? Big asking. No. Nuclear radiation, something's happening. So here's these guys help us define what close means. So here's the idea. Let me write down some formal stuff. Given epsilon greater than 0. So epsilon is a distance. So of course it's going to be greater than 0. So given some epsilon greater than 0. Somebody comes along and says, okay, if that really is the limit, then I want you to find, you're going to love this, I want you to find some neighborhood of A where all the outputs are within some neighborhood of L. So this is epsilon. This distance here is epsilon. So I'm going to tell you how close to L I want you to be. No matter what epsilon I give you, you should always be able to find a neighborhood around X that's always that close. So visually, this is what that would mean. So here, see how every input in here ends up with an output in there. Okay, let me stop for a second. I just want that to permeate your brain. No matter how small, if this really is the limit, no matter how small somebody makes this, I'm always going to be able to find something that stays within that, if that really is the limit. So let me show you a silly example, a counterexample. Silly kind of counterexample. Let's say this is going on, and I think the limit is here. Right? Let's say I think the limit is there. You guys understand what I'm saying? I think that's the limit. So they say, okay, here, let me give you a little range. What range do I make so I'm always within this much? Well, there's nothing. If I go here, I'm there. Am I ever inside there? Am I ever getting outputs that are in that? So that would be a quick, like, oh shit, I'm wrong. If that really is the limit, no matter how small they make epsilon, no matter how small they make that around L, I should always be able to find an area around A that ends up in there. This is the extreme, like, this is the opposite of that. This is like, I can't, holy shit. Maybe. That's the idea. Sorry. So given epsilon greater than 0, we must find delta greater than 0. So here's delta. Yeah. That's the distance that finds that. And believe it or not, that's not my word. That is the actual word, neighborhood. It's the neighborhood around A. I always kind of enjoyed that. I like that. What a neighborhood. We must find delta greater than 0. So given some distance from the output, I always have to be able to find some distance from the input where all those inputs fit within that range around the output. If that really is the limit, that should be doable. So at least if I stopped right now and said, that's it, what's U4? Let's forget U4. And you guys are like, yeah, say that for real, Jeff. You'd at least understand what epsilon and delta represent. They are distances. They are technically very tiny, tiny distances. Yes?
So is delta the space or the A neighborhood?
Yes. So delta is the X. Epsilon is the Y. Always. Unless it's defined some other way. But these are kind of set up to be that. Right? Like, is this always the x-axis? Well, if I don't say, you're going to say it's the x-axis. Unless I say, no, it's t. So yes, this is always true unless some idiot comes along and says, no, I want it this way. Yes?
When you say epsilon more than 0,
Say again, sorry?
when you add the like greater than 0,
Just to make sure that what this says is, what this really means, since epsilon is a distance, it's always positive. So if I'm given any epsilon, because epsilon is greater than 0, it's a distance. So given any epsilon is another way I could say it, but that's too many letters for math people. That's the way to say any epsilon. We must find some delta so that this works. If that really is the limit, I can always find it. I want you to be this close. Okay, there you go. I want you to be this close. Okay, there you go. If that really is not the limit, I want you to be this, this close. Oh, shit, I can't do it. Then it's not the limit. Okay, maybe. And again, we're just starting. You haven't even seen what the proof looks like yet. Given epsilon greater than 0, we must find delta greater than 0 so that, when that distance is less than delta, so that when I'm in that neighborhood, so in mathfish, that's this. In English, this says when I'm in the neighborhood of A. Then what must be true about the outputs? They have to be in the neighborhood of alpha. So if I have an X that's in here, if I have an X that's in this neighborhood, well, what does it take for an X to be in that neighborhood? The distance between it and A has to be less than delta. That's how you get in that neighborhood. The output must be in this neighborhood. Well, how do you define the distance between the f of x and L has to be less than epsilon? Bam. I like it. All right. That's it. Now watch. Here's how it works. The thing that feels like cheating is this is a construction proof, and they very often feel like cheating. I'm going to construct the delta that works, and then I'm going to use it and show that it works. So it's going to kind of feel like you're doing something twice, but you still better do it twice. Right? The side work is not the proof. It's just constructing what delta has to be. So watch how this works. Let's see. Let's do an actual problem. That'd be nice, Jeff. What do you got, Jeff? So prove that the limit is x equals to 5 of 4x minus 11 is 9. Now, is that true? Yeah, always kind of double check, especially when I make one up on the fly. And make sure Jeff has got his multiplication and subtraction working. Okay, now on one level, I know a lot of you guys are like, I'm done. I put a 5 in. Leave me alone. But, let me try to get this across. I did assign one or two problems that go beyond linear. Do you see how this function is linear? Okay. The minute the function gets funkier, then the proof involves a few more steps. So we are dealing with just linear functions. Also, this idea we're setting aside is going to be used in larger proofs to prove bigger things. So this proof by itself, it seems like we're done. Plug a 5 in, I get 9. Next. But this is sort of, if you're anybody like a math major, or you came in thinking you would be, and then I've already convinced you not to be. Or if you were a math major, you would get to a point in your career where you have to prove that 2 plus 2 is 4. You couldn't assume it was. You'd have to prove it using very basic principles. We all assume it is, or prove radical 2 is irrational. Right? That's a little more known proof. Prove that radical 2 is irrational, that kind of thing. You can't just assume it is. You have to actually prove it. All right. So this is easy. I know it's true. Okay, so this should work. This proof should work. The first thing you do is you do some side work. Let me do it. And what is it we need to show? Given epsilon greater than 0, we need to find delta greater than 0 so that if, let me see if we can write this. We need to find delta greater than 0 so that if x minus what? What's a? 5 is less than delta, then what's f of x? That's L. So here's L. That's the limit. Here is f of x. Here is A. That's just identifying those parts. So given this epsilon greater than 0, given some distance around the limit, the supposed limit, I need to always be able to find a distance around the input that ends up within that range. If that really is the limit, I should be able to do that. Like it. So what am I missing here? Yeah, 4x minus 11. Less than. So that's the epsilon is all about the outputs. Delta is all about the inputs. Okay, I like it. Now, this is just a statement of what we want to do. So that's going to get the side work started. So look, I can start here. So if I start here, if I start where I want to be, this is why it feels like cheating. Start at 4x minus 11 minus 9. Help me out. What can I do? Still sideways. Yeah, what do you get? Down there. Can I do some more? What can I take out of here? 4. So if I take a 4 and divide by 4, what do I get? So what do I want to let delta be then? Yes. So somebody comes along and says, I want you to be within 1 of your supposed limit. And we're like, all right, I'll just stay within 1/4 of my input. Whatever they make epsilon. So doesn't this make sense? I want what I respond to them with to depend on what number they gave me. So if they give me some really small number, I'm going to cut it down by 4, and that's going to guarantee that all my inputs end up in that range around the output, around the limit. So that's what's going to happen. Now, like I said, this is why when you do this problem, it feels a little bit like cheating. Some of you guys might realize it's always going to be the freaking slope. You blah, 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 blah. I still need to see this side work. The minute I make this squared, or square root, oh my God, anything that's not linear, the difficulty jumps way the shit up. So I think that's why I only gave 1 or 2 of those kinds. They have several examples in this section. I wanted to give some of you guys a bit of a challenge. If you're at all curious, it gets really kind of nifty. Lines are almost too easy. Anything else is almost too hard. It's kind of crazy. So how do I finish this up? So this is not the proof. This is side work. You don't stop here. What's the proof? Given epsilon greater than 0. So here's the proof. Given epsilon greater than 0, let delta equal what? What do we say? Okay. What do I want delta to be so that this is true? Yeah, epsilon over 4. I like it. So let delta equal epsilon over 4. This is why it feels like cheating. The side work, I constructed what my response is due. How do I prove it, though? I've got to go forward. This is kind of backwards. I've got to go forward through this proof. Given this, let delta be that we found it. Then, you can do it. If this is less than delta, which means this is less than epsilon over 4. Now, why? This is, again, this feels like you're cheating or repeating yourself. It's actually nice. Just undo all this shit we just did. Multiply by 4. Break this up into 4x minus 11 minus 9. And this is f of x minus L. Right? This is f of x. And this is the limit. So given epsilon greater than 0, we found a delta so that when my x's are that close to 5, my outputs are that close to 9. As close as that dude wanted me to be. Whoever it was that came along and said, oh, yeah, what if the epsilon is 0.03? All right, I'm going to let delta be 0.03 divided by 4. Maybe. Let me... All right, if you look, let's do this. On the other side of that group worksheet, some of you guys have noticed this. I gave you another example of everything worked out, and then I have a problem there at the bottom I want you to try. So go ahead and try that problem at the bottom. We'll do a problem visually, and then we'll probably call it a day at that point. Maybe we'll see what time it is. We'll get to this